Really excited to talk about the world's best subject, and that's geospatial technologies and geographic information systems. And what I'm going to try to do is talk a little bit in terms of a broad overview about geospatial technologies, why I think they're important, why I think they're important for students to learn about and practice, give you a little bit of an idea of maybe where we're headed in terms of the future with geospatial technologies and some of the requisite skills, the skill set that's changing over time. What we need to know today to effectively apply geospatial technologies is vastly different than it was in the late 1980s, early 1990s when I was learning about geospatial technologies. And then time permitting, I'd like to wrap up with a couple of quick examples of the application, hopefully the effective application of geospatial technologies in some grassland monitoring efforts that we're performing at Fort Riley and would like to do for a number of Department of Defense military installations, helping them manage their military training lands in a more sustainable way. Two fists there. Maybe I could start off by asking, how many of you guys use GIS? Okay. Everybody should raise their hand. Whether you think you're using GIS or not, chances are you interact with GIS or geospatial technologies a lot more than you realize. Probably the easy example is Google Maps, right? How many of you have not looked up something on Google Maps or gotten directions on how to get from Manhattan to some high school in Topeka to watch a high school soccer game because you didn't know how to get there? Okay. A good classic example of geographic information system technology in action for important practical problem solving. Right? The backbone of this web application is GIS and network analysis that allows us to go in, type our current location in, that geolocates on a map, where we want to go, again, another geolocation process, and then sometimes finding the most effective route between point A and point B. Sometimes we rely on those kind of things for less important bits of information. Any British English Premier League fans, soccer fans in here? All right, so when the 2015-16 season kicked off, we had 3 new teams enter into the Premier League, the ones that finished at the top of the lower level in England. And I had no idea where Watford was. Does anybody know where Watford is? Now, Watford's in the northwest of London. Okay. So again, another example, simple example, fun example of using maps, geocoded information to find out information. Maybe a little bit more importantly, we can see examples like this, which represents the 2010 population in a dot map format for the entire continental United States. And if you look at this website that's highlighted there at the top, actually it's a wonderful web application that allows you to really dive deep into the population data and see with incredible detail the distribution of people by race across the United States. Some fascinating patterns as you compare cities like San Francisco to Chicago to Atlanta. Okay. Maybe something more important, more current in terms of the news. An example here of sea surface temperature anomalies from this morning. Downloaded this this morning, highlighting our current El Niño cycle of elevated sea surface temperatures across the equatorial region. So again, images that you probably see or could easily see, all of which rely in some fashion, all or in part, on geospatial technologies. Ozone hole formation as it gets stronger with the polar vortex over Antarctica from from August through September. Drought conditions. We're fortunate this year in Kansas maybe to be on our way out of a drought over the last couple of years, but the poor folks on the West Coast certainly are suffering. Okay. Again, all examples, hopefully decent introductory examples where geospatial technologies were at the core of those products. I struggled a little bit when I was asked to talk about GIS and geospatial technologies because I often don't know where to draw the boundary of that topic. So I've started over the last couple of years not thinking in terms of just GIS or not just in terms of satellite remote sensing or global positioning systems, but lumping them into that category of geospatial technologies. They're all related, right? They all are ways for us to acquire information, locational information, thematic information about the world around us. If we factor in that kind of nebulous other category, which shows a three-dimensional LiDAR picture of a forest canopy, we've got now and going into the future some really novel ways to measure things and represent that in graphic and map format. But again, I don't really know where to draw the boundaries here. I think of GIS really forming the core. I think GIS is super important because it's a little bit different than your GPS or your remote sensing. With GPS and remote sensing, really those are technologies that measure something. With a GPS, whether we've got our cell phone or a GPS receiver, it's giving us information on where we are. Satellite images, aerial photography, images captured by unmanned systems are photographs of the surface. GIS takes that information and allows us to do something, hopefully, of benefit. The good old but boring textbook definition of GIS is an automated system to capture, store, retrieve, manipulate, analyze, and display geographic information. Not very exciting, but important and a pretty accurate definition of what GIS does. And when I think of GIS, I think of that image here on the right of the screen. Right? Our ability to take digital data acquired perhaps from a GPS, perhaps from a remote sensing platform, organize it inside of a computer, display it on our computer screens, manipulate the data, hopefully for positive purposes, overlay it, and ultimately ask a series of important geographic questions. And questions that I really don't think there's an alternative source or an alternative technology that performs the same service for us. Right? We can't ask these questions of data we store in a spreadsheet, for example. Where are particular features found? Where do certain conditions apply? We ask these questions in a live, interactive way with our digital data. What patterns exist? We can measure those patterns. What changes have occurred over time? So we've got the ability to monitor things and changes as they occur. We can look at different scenarios, make changes in the digital data, and see what impact that has on decisions or future conditions. Okay. So very, very, very important. And the part of GIS that ultimately gives GIS its true power is the relational database. Okay. Again, not always the most entertaining topic to discuss are databases. Okay. We've transitioned over the last 6 years from storing data on our individual computers in proprietary formats to universal formats in large commercial relational databases. And that allows us to do a number of things that until recently hasn't been possible before. Okay? We can be sitting at our desk in our office or in a computer lab, writing data to a database and having someone from across the world accessing that data as it becomes available, sharing that data in a GIS framework. If we're a little bit more advanced in our GIS capabilities, we can be working with the data and developing analytical procedures, models, to do something useful with that data. We can publish those models in a special format called a web service, which essentially is a small software program. Make that model available to people that we want or the general public. And again, people can grab that web service, access your digital data in a commercial database, and solve problems. You can be in the field with your cell phone or a mobile computing platform, and again, collecting data, writing it live to a database, and doing analysis on it all in one simple step, relatively. Because the relational database is the backbone of the GIS, it's opening up the door to some other interesting ways to acquire data. And I find this especially interesting because it's moving us closer to the possibility of doing all of our analysis, or at least much of our analysis, not after the fact, but in real time. We can have distributed sensor networks across an area of interest. We can have a couple of examples here. Maybe we've got an unmanned system flying over the area, weather stations, cameras, seismic sensors. Boy, the possibilities are endless in terms of what can be designed as a sensor and put in the field. As long as there's an internet connection or that sensor is in range of a cell tower, we can be transmitting that data live from the field into a database and watching that in our office and doing analysis on it all at the same time. So that's, I think, really an exciting possibility here as we move forward. Okay. One example of a distributed sensor network, and this is, I cheated a little bit with this, is the USGS earthquake mapping site. So you can go to the website and see for the last day, last 5 days, last week, whatever time period you put in, earthquakes that are happening around the world. Okay, again, this is all being collected by distributed sensor networks. Eventually that data works its way into a database. It's harvested by a GIS system and published as a service inside of a web application that we consume inside of a good old web browser. Okay? So in this case, my cheat here was I went in and I queried for all the earthquakes in Kansas between January 1st and September 17th of this year. And that was the result, magnitude 1 or higher. And that was the result. And I zoomed out a little bit because I wanted to highlight the spatial pattern that was formed by the earthquakes. Okay. Over 3,000 magnitude 1 or higher earthquakes. Where is that seismic activity kind of centered at? Yes, Oklahoma, but what's going on in Oklahoma? Yeah, it's a lot of fracking going on in that area. In fact, was it this spring that we had the earthquake that was felt here in Manhattan, I think? That was centered just southwest of Wichita. Okay. Again, good example of a distributed sensor network. So I pulled up this morning as well another example of distributed sensors from a class project in our Internet GIS class. So this was the view from the KDOT camera, highway camera system at the Manhattan exit, the Junction City exit, and the Colorado exit. Okay. So again, images that we are free to harvest from a database that KDOT maintains and use for whatever purpose we think is important. Okay. It wasn't raining at that time, or snow. Usually when I look at the Colorado image, it's snowing, but I guess we're still too early. Okay. So if you're planning that trip west, looks good so far. Okay. Maybe the most common example of a distributed sensor network is what we carry around in our pockets all the time, our cell phone. If you have any social media applications installed, or you like to Yelp reviews from Windows, or use an application like Foursquare, chances are you've agreed to allow your location to be shared with others. So you can pull up your cell phone, see where you're at, see where things you might be interested in are at, friends, other places, and acquire information that way. People as distributed sensor networks is something that is becoming increasingly used from a research perspective. Our ability to leverage the power of people roaming around in the world to collect information for us. So we'll see more and more human sensors being brought into the research fold going forward. Okay. Most people who do GIS, kind of their mode of operation, their mindset, focuses around what I'll call the 3 M's. And that's mapping, monitoring, and modeling. Most GIS applications, geospatial technology applications, feature one or more of these activities. And the example I'm trying to show here encompasses all of those things. We could acquire data ourselves or download from sources like the USGS, land use, land cover information for the Topeka to Kansas City area and try to map out the developed areas. okay, as it is now, or as it was in 2006, and then use quantitative methods to forecast what those urban areas might look like going into the future. Okay. Maybe bringing in that other category of geospatial technologies to allow us to do that. We can take current conditions, projected future conditions, and use that to create models like flood hazards, forecasting. What would particular patterns of land use development yield in terms of increased chances for flooding? You know, something that even the city of Manhattan would certainly benefit from to better evaluate our own development policies. Okay. So we can generate maps, right? Pictures of whatever system that we're working with, which are incredibly powerful in and of themselves. We can monitor conditions over time or forecast conditions into the future or hindcast conditions going into the past. And then we can bring in good, tried and true, or novel quantitative and modeling methods to do something really interesting with that geographic data. Okay. So that's my brief overview of geospatial technologies. Wanted to share just a couple of examples here of geospatial technologies in action. And again, the dividing line between GIS, remote sensing, GPS, and other categories here isn't necessarily going to be clear. Okay? But GIS, again, is at the core of everything that you'll see moving forward, even though probably the most common feature that you'll see is satellite images. Okay? So we've been working over the last 8 years or so with Fort Riley and the U.S. Army Corps of Engineers to help them do a better job and less costly job of monitoring military training lands. The folks who manage military lands have quite frankly, a very unenviable task. They've got to meet the requirement that allows military units to use that land so that they can prepare for their wartime missions. But they want to do so in a way that land is still going to be relatively intact going into the future. And it's not going to be a situation where the military can simply just purchase up land as they consume it and waste it and leave it be. So we proposed to the Corps of Engineers a geospatial technology approach. Okay? We wanted to be able to monitor, assess, identify trends and some key environmental indicators, not a year after it happened, after we collected data, analyzed it, and wrote a report, but within a matter of minutes of the data becoming available. Okay? The notion here is we wanted to give them maybe a 70 or 80% correct picture of the condition of their lands right now, rather than a 95 or 99% correct solution months after the fact. Get that information into the hands of the land managers when they can make decisions to perhaps counteract some bad things that might be happening within their training lands. And this really hadn't been done before on military land. So we started at square one in terms of looking at ways that we could simply monitor current grassland conditions. And Fort Riley was our initial focus, so grasslands was an area of emphasis for us. So we wanted to be able to have a system in place for them to monitor the grassland conditions at Fort Riley. And also, while we were doing that, slowly over time, build up some baseline data where we could document what was normal for Fort Riley. Because no one could answer that question for us in terms of what are grasslands typically like at Fort Riley. I don't know. Right? It's hard to make management decisions if you don't know what's typical. As part of the process as well, we wanted to look over a long period of time to see if we could detect any trends in grassland conditions. Are the grasslands getting better? Are the grasslands getting worse? Again, as part of that effort, we wanted to go in and calculate phenometrics for both military and non-military grasslands. I'll define what phenometrics are here in a moment, but again, we wanted to see if we could quantify some characteristics about military and non-military lands here locally relative to the typical development of the vegetation, that told us something interesting. Are military lands and the vegetation on military lands different? Do they behave differently? Are they impacted differently than the vegetation on non-military lands? Ultimately, where we're headed with this research is trying to be able to develop this monitoring system where if we see change, we're able to attribute that change to a specific military activity. Okay, so we can untangle change from weather effects or climate effects or non-military activities. Okay, so things that are relevant to the military land managers, we can pinpoint the cause of the change that we're seeing. We're not quite there yet, but we're certainly closer now than we were a few years ago. So our study area is Fort Riley. All the examples we'll see here of Fort Riley are from Fort Riley. Fort Riley is a pretty large military installation, about 64,000 hectares. It is kind of in the top third of U.S. Army installations in the country in terms of land area. So it's very important to the Army as a site for mechanized training. And what I mean by mechanized is they like to run their tanks and armored vehicles all around Fort Riley. In particular, this area, the northwest part of the installation, north of about this line and west of the artillery and mortar impact area. That area gets significant use by military vehicles. So just to give you an idea of what this looks like, let's see if this works. Show a very short video. And this is all from Fort Riley. You can see some of the evidence of the military training and its impact on the vegetation, crossing streams, traveling parallel to streams, changing the entire surface hydrology, the drainage characteristics of the watersheds at the fort. Tanks aren't necessarily great for vegetation, especially when it's wet. That's a tow truck for tanks. Digging large holes. Shearing off vegetation, churning up the upper part of the soil profile, doing lots of good things like that out at the fort. So again, we wanted to have this geospatial technology approach, something that we could have these very frequent looks at the training area, quickly identify any problems, so that way if there was a need to go out and fix areas, perhaps to smooth out this area, replant with grass seed to help prevent erosion, that those land managers have that information quickly when they can make a bigger difference. So one of the primary data sources that we used for a lot of our efforts came from a satellite. It came from the Terra satellite and the MODIS sensor, the Moderate Imaging Spectrometer. It's a moderate resolution sensor. It captures images at a 250 meter by 250 meter pixel. So it's not really high spatial resolution. Those pixels translate into an area of about 6¼ hectares. And the particular satellite product we've really relied heavily upon is called a 16-day composite normalized difference vegetation index data set. So the Terra satellite that contains one of the two MODIS sensors actually passes by overhead every day, sometime in the morning. I can't remember exactly when. So we get a daily image from this sensor. The 16-day composite allows us to collect the best, from each image, the best pixel over those 16 days. And it helps us really just eliminate the impact of cloud cover. Okay, so at the end of that 16-day composite period, the hope is, and this is usually the case, is we have a completely cloud-free image. And the NDVI, or Normalized Difference Vegetation Index piece, is a measure of surface greenness. Okay, so it actually collects information in the red and near-infrared part of the electromagnetic spectrum. It ratios that data, and the end result is a measure of greenness. That measure of greenness, in turn, is used as a proxy for vegetation condition. Lots of studies have shown that NDVI correlates very well, most of the time, with things like above ground biomass or leaf area index. So we're using NDVI in that context. We've had MODIS data, complete annual time series of MODIS data since 2001, although the first MODIS images were acquired in February of 2000. And with that 16-day composite period, we're able to acquire 23 useful images every year, about 2 per month. Okay. So every 16 days, we're getting another record, another image of what the grassland condition for Fort Riley, in this case, what it looks like. Okay. Just to give you an idea of what a MODIS image looks like, this is one. The screenshot on your right is actually the entire MODIS scene. So as the satellite goes in its orbit, it captures snapshots, the pictures. So one scene of that is shown there, that small box on the right. Okay, so it's a large geographic area. Again, each pixel's about 6¼ hectares. And that little red box in the upper center is highlighting us right here in Manhattan. And that's on the left is an enlarged part of that. And it's easy to pick out Milford Reservoir and Tuttle Creek Reservoir there. And there's good old Manhattan with Fort Riley in between the two reservoirs. So this image, again, it's a black and white image. It's NDVI still, scaled between values of 0 and 255, an 8-bit digital number image. The lighter the pixel, the lighter the color of each pixel, the greener the surface. The darker, the less green. So you see those water areas show up very dark because there's no plants in those areas. If you look here in the complete scene, what is this feature? Any ideas? Again, that little red box in the top center is us here in Riley County. If you were thinking Gulf of Mexico, you were thinking correctly. Yeah, so it's a large geographic area there. So one of the first things that we have to do in this automated processing chain to help the folks at Fort Riley is acquire the data and immediately get rid of the data that we don't want. So every 16 days, with a click of the button on our computer, we download the image, we clip out the area of interest, Fort Riley, and we do some cartographic work to change the map projection associated with this. One of the reasons why that 16-day composite period image is so important for us is, and here we don't see any clouds, right? Every image that's acquired in that 16-day period, we're grabbing the best pixels from each one of those images. Here is a daily image from the morning of August 18th, one of the days inside that previous composite period, just highlighting the cloud cover that was present there. And again, it's a little bit harder to see, but that red box up here, that's where we are. Okay? So if we were relying on daily images to do this analysis, more days than we'd like, we'd be foiled by cloud cover. So that 16-day composite period image gives us, I think, a pretty dense collection of data during the course of a year. It's reliable and contains lots of good information. Okay. So after we do all of that cartographic work inside of a GIS, we can create maps that look like this. These two maps are from two adjacent composite periods from a few years ago, 2010. But the map on the left is from June 10th through June 25th, that composite period. And the other one is from June 26th through the 11th of July. So again, every 16 days we see an image that looks like this at the peak of summertime. So we see lots of green. Now here we've changed it from black and white to brown to green to highlight the green nature. But other than that, they're kind of boring images. They don't tell us a whole lot about what's going on. Everything looks pretty green. If you're familiar with Fort Riley at all, any guesses as to what this area might be? Or maybe down here? The developed areas out at the fort. Kind of the horseshoe-shaped area is Custer Hill, where a lot of the office buildings are for the military units. and that area off to the east, the southeast, is the rail yard out at Fort Riley. Okay, so you can see the contrast between those different land covers. But if you look within most of the training areas, not a real interesting image. It's much better to apply some simple map algebra to those images. So I'll show an example here of the processing there shown at the top of this slide, where we take, say, a current composite period image and subtract from it the NDVI values, again at the pixel level, from the previous composite. And what that allows us to do is very quickly see areas that have changed quite a bit from one time period to the next. We also do the same thing, sort of the same thing that's illustrated below, where we take a current composite image and subtract from it the mean of all previous composite periods from that same time. Okay? And that gives us a slightly different view of what's going on at Fort Riley. It compares now to what's typical. Okay? But that the abrupt change image has been shown in practice to be really useful to the folks out at Fort Riley. Another couple composite period images here, but these are the abrupt change, simple image differencing examples. So we've got one here from 26 June through 11 July, and one of the features that really pops out on this, most of this area is white, so there's not much going on in terms of change. Areas in red show a negative change, so the surface has gotten less green. Areas in green are where the surface has gotten more green. Okay, so most of Fort Riley, not much going on here, except on the top, right? What's this area? Which was very strange for the end of June, beginning of July, to see a sudden surge in greenness anywhere other than perhaps some sort of agricultural field, but especially in the grasslands at Fort Riley. So when we computed this, this data actually is live on a web application that the people at Fort Riley look at. They saw this and went, oh, that's post-construction grass seeding. So they had been doing a lot of work up here in their tank gunnery range, and in that intervening 16-day period, they replanted some grass, and we were able to capture that with that moderate resolution satellite image. Any ideas what's going on in the other map shown here from August 13th through the 29th? An area where between two composite periods we've had a pretty significant decline in surface greenness. It was a fire. Yeah. Each of the little squares, it might be hard to see on the map, each of the little squares you see there are our administrative boundaries at Fort Riley called training areas. And for whatever reason, they decided they were going to burn that training area. And we captured that on the change image. So even though our pixel resolution, or our image resolution, is fairly coarse, we're able to detect changes that are relevant for the folks at Fort Riley. So again, every 16 days we're seeing images of this. Again, I mentioned before, all the data that we collect, all the data that we've seen and the things that you will see are done in a GIS using a lot of satellite remote sensing. It's all stored in a database. They're published as these web services, okay, all just a couple of button clicks inside of a GIS. And then we send those images into a web application. Okay, so the users at Fort Riley don't need special software. They don't have to buy special software. They just need Firefox or Chrome or Internet Explorer and a web address. And the web address is shown there at the bottom. It's a public site, and you can, if you're interested in the grassland condition at Fort Riley or Konza Prairie, you can see that and updates of every 16 days. The image that we see here is relatively recent from here in 2015, the composite period beginning June 26th. It's that abrupt change image. So you see there's lots more going on here than the previous abrupt change that I showed you. It's a little bit hidden, but there was a lot of change right here. And even to this day, I don't know what caused that necessarily. It could have had soldiers firing weapons at weapon ranges. But we saw a lot of negative change. And we've got built into that web application some of those analytical tools that I mentioned before. So it might be of interest to the land managers of Fort Riley to say, okay, if we've got some removal of vegetation in these areas, that's going to expose the soil surface. We might have elevated rates of erosion. Within that watershed, where might we see increased sediment loads in the stream? So the tool that they can use is a simple tool. They click on this button, click on the outlet of a watershed, and we delineate the boundaries of that watershed on the fly. So they may want to come over here and start looking at sediment levels in the stream to make sure they're still within compliance for regulations. Okay. So in terms of looking at those greenness images, those 16-day composite NDVI values, we were also just graphing the data. Again, part of our work was to determine what typical conditions were like at Fort Riley. So if we grabbed all the pixels for Fort Riley inside the boundary of Fort Riley and calculated the mean NDVI for each composite period over a 14-year period from 2001 through 2014, we're able to create kind of a mean phenology curve for Fort Riley. So the darker blue line here in the middle is the average. And I've got error bars there. It shows a little bit of it gives you an idea of the variability in NDVI for each of those 23 composite periods. The line up above is the maximum recorded NDVI over that 14-year period across all 23 composite periods. And the lower line is the minimum. Okay. So we can do a better job of characterizing vegetation development at Fort Riley by looking at it this way, and maybe appreciate what's going on at Fort Riley more by looking at the same data, but data that was collected for Kanza Prairie, okay, which shows that Fort Riley is much more variable than Kanza. NDVI values at Kanza are within a much tighter range across the entire year and within each composite period. Another way that we can look at this phenology data is to look within each year, and as we collect data across all composite periods, we can compare current NDVI for Fort Riley to the normal, and now we've got 14 complete years of data for Fort Riley. It's becoming more meaningful to do that. And then the bar charts show deviations from normal. Okay, so in 2012, we had some precipitation in the spring that allowed greenness to explode and be much higher than normal. But if anybody remembers the summer of 2012, it was really dry that year. Okay, so we saw typical greenness at Fort Riley much lower than average. Then we had one small precipitation event in August, and it was just in time for the grasses to take advantage of that, and you saw a little surge there. Okay. We can drill down a little bit deeper into that same data, and instead of looking at Fort Riley as a whole, taking the average of all the pixels inside of Fort Riley, we can look at individual training areas as well. So the graph on the left shows the green line and the red line represent plus and minus 5% of the normal for Fort Riley. Okay, the same kind of data we saw before, plus or minus 5%. The dashed lines represent two training areas indicated in stars on the map on the right, so we can track what's going on at a much smaller scale. Okay, two training areas that get a lot of use out at Fort Riley, and we can see their development and use the reference lines of plus or minus 5% of the normal as a management tool. You know, if we're outside of those boundaries, we might want to examine how we're using those training areas. You know, in August, we see both training areas well below that minimum threshold. Okay, we might want to eliminate training from that area for a while if it's possible. So again, an effort here to create some decision support tools for the land managers. If we wanted to, we could drill down even further and look at individual pixels inside of each of those training areas as well, and break our decision making down to the 6¼ hectare scale. That's a lot of graphs though. So in looking at those phenology curves, we got real interested in maybe exploring that idea a little bit more rigorously and comparing Fort Riley phenology with how grasses develop at Kanza Prairie. And within Fort Riley, how training areas that get a lot of use might differ from training areas that get relatively low amounts of vehicle traffic, for example. So we took a time series of those very same MODIS 16-day NDVI composites, this time just for the period of 2001 through 2012, so 23 times 12 images. We did some processing within a computer program that allowed us to take that raw data, develop the phenology curves, and assign dates or values to key parts of that development. And I try to show that here on the left side, excuse me, the right side, which is a kind of a typical phenology curve. With our computer program, we're able to give a date for when greenness begins, the end of greenness, accumulated NDVI is the area under the curve, maximum NDVI, and some other things, other quantitative measurements about that curve. So we processed all the data, harvested all the results, did a little bit of statistical analysis, and long story short, Fort Riley is different from Kanza. Probably not a surprising result necessarily, but we didn't have any proof to show that before. Okay. So here's just two examples from two different phenometrics. The length of the growing season, so the number of days between the onset of greenness and the end of greenness, and the small seasonal integral, the area under the curve. And that data here for Fort Riley is in the dashed red line. Kanza is the blue. And for growing season length, we can see that at Kanza, the growing season length is pretty compressed. Okay. Whereas at Fort Riley, we have a little bit, but a statistically significant little bit, earlier onset of greenness, and the growing season lasts longer at Fort Riley, which suggests to us differences in species composition between the two sites. Maybe some more cool season species at Fort Riley as a result of the disturbances that go on there. The other one shows that accumulated NDVI. And again, at Kanza, you see a compressed range where more pixels have higher NDVI values than Fort Riley. Again, probably something you could have guessed at before the analysis began, but now we have some quantitative numbers to attach to those differences. And in fact, we repeated that analysis for what we call normal years, cool wet years, and hot dry years, and we saw differences consistently across all three types of those seasons. We also looked internally within Fort Riley and saw that there were statistically significant differences for all the phenometrics between training areas that were used heavily versus those that got a little bit less usage. So again, here we've got some more evidence that allows us to translate our satellite imagery processed inside of a GIS and other types of programs and what that means in terms of military impacts. One final thing is we did a long-term analysis of grassland greenness trends for Fort Riley. So again, another example where satellite images were the input. We had some other tools in the form of software programs that allowed us to process hundreds of these images and as a product of that, be able to detect for every pixel in that image the linear trend in greenness over a 10 or 12 year period. I can't remember, I think it was a 10-year period for this study. So for every pixel, we were able to say, oh, we've got a statistically significant negative trend over that decade. And even within that, we're able to detect whether there was a significant break in that trend. Did something happen at a particular time that caused greenness to be reduced dramatically, or in some cases, increased dramatically here. Right? So this example shows a pixel at Fort Riley with a negative trend from training area 77. And the other one here is from training area 56, which actually shows a statistically significant positive trend. Okay. So we processed all this pixel level information over that 10-year period and allows us to produce maps that look like this, which is probably more interesting. Right. So at Fort Riley, the majority of the installation from 2001 through 2010 actually experienced a decline in greenness. And we've got Kanza Prairie there in the upper right as a point of comparison. It's a different story at Kanza Prairie. The majority of Kanza saw improved greenness or no change. So we've got two different things manifesting themselves here across the military lands versus the non-military lands. We were actually very surprised by this. What was going on in the world between 2001 and 2010? Actually, what's still going on around the world? There wasn't many people at Fort Riley. There were a lot of people assigned to Fort Riley, but the vast majority of the soldiers who live and work there were deployed to various parts of the world. So there wasn't much going on training-wise during this decade, yet we still saw the majority of the installation declining in condition, as measured by changes in NDVI. So that was the surprising piece. So perhaps what we're seeing here is an impact of previous training from previous times. Perhaps soil compaction is helping to contribute to this declining trend in greenness, not necessarily just current training activities. Okay. All right, so I'll skip that. So the one thing I want to leave you with, and hopefully we'll have maybe a little bit of time for questions, is I think geospatial technologies and a couple of other areas arguably could be the single most important thing in your environmental science toolkit. Okay. Geospatial technologies, hopefully with a couple of examples that I showed today, certainly are important. The other two areas that are becoming increasingly critical as we deal with larger volumes of data in our typical projects is competence with databases, a little bit of programming skills, and a good handle on lots of different quantitative analysis and modeling techniques. Right? If you can bring a little bit of expertise in all of those three areas, your knowledge of physical, biological, and human systems all together, you'll be in pretty good shape moving forward. Okay. Thank you very much. Question or two? Yes, sir.
Could you redefine
phenometrics? Phenometrics, phenology would be the study of vegetation development. So a phenometric would be a measurement about that development. So phenometrics that we looked at were things like the date when greenness started, the end of the growing season, the length of the growing season. In that curve, which is usually a unimodal curve here in this part of the world, the maximum NDVI. So things that we could capture and do some statistical analysis on later.
Shawn, you hinted at continuing change within the GI science area. We now have 3D printers. Is the visualization component one that's going to continue to evolve over time with respect to our ability to help make sense of this data?
Yeah. I mean, if anybody has seen, and maybe I'll reveal a little bit about my personality, any of the Lord of the Rings trilogy movies, right? I almost had that on my slide. Geospatial technologies. How were those scenes and those people moved around in the scenes? Geocomputational methods and GIS-based visualization techniques. But yes, and what's really interesting about that, John, is visualization techniques and the role they will play in helping us better understand really, really dense, multi-dimensional data sets. So going beyond maybe some of the simple maps that I showed here of a single feature at a single time, but how do we create a visual product that shows many more dimensions, both 2D and 3D types of dimensions, as well as the number of variables or attributes associated with that. Lots of challenges with that. But we all know pictures are important and our ability to synthesize and understand information better.
Let's give Dr. Hutchinson a hand. Thank you.
Thank you. If anybody's interested, I just showed this screen. We do offer an undergraduate certificate in GIS. So the course requirements are shown there. If anybody has any questions about that, I would be happy to answer. Okay. Thank you.